The length of plane curves. So how do we calculate or measure the length of curves in the plane? In this case, suppose C is a curve given parametrically by the equation x equals to f of t and y equals to g of t, and t is bounded between 2 points A and B inclusive. For example, you can assume t is an angle, or t is time, or anything else in the context of the question. Suppose you're interested in calculating the length of the curve starting at this point and stopping at the terminal point here. What is this length? Well, if you think about it algebraically, you might be interested in using some approximation using some line segments. So consider a line segment connecting these 2 points together. We can easily measure the line segment and then calculate the length and do a nice approximation for this curve. How? We're going to use Pythagorean theorem. Pythagorean theorem says if you have a right triangle and if you have the measurement of 2 legs, you can easily calculate the hypotenuse. How? A squared plus b squared is equal to c squared, or in terms, c is the square root of a squared plus b squared. So basically, to measure or approximate the length of the blue curve here, you can calculate the length of this line segment using delta x and delta y and Pythagorean theorem and have a nice approximation here. In general, when you're trying to approximate the length of this line segment here, we have the function. We know that the function f is associated to x and function g is associated to y. Suppose the terminal point is denoted by p sub k and it's equal to x value, which is f of tk, and the y value, which is g of tk. The initial point here is denoted by p of k minus 1, which is x and y. Your x is now denoted by f of tk minus 1, and your g tk minus 1 is in terms of y value. Well, you have your x values, you have your y values, so you can calculate delta x and delta y and drive a formula. By using Pythagorean theorem, if you have the initial point x1, y1, and the terminal point x2, y2, the distance between x1 and x2 is denoted by the absolute value of x2 minus x1, and the distance between y1 and y2 is y2 minus y1 in absolute value, because it's just the distance. Now, d squared, which is equal to a squared plus b squared, can be written as x2 minus x1 to the second power plus y2 minus y1 to the second power. So d, which is the square root of the quantity on the right-hand side, is the positive sign because d as the distance cannot be negative. It is the square root of x2 minus x1 to the second plus y2 minus y1 to the second power. So we are following the Pythagorean theorem for a right triangle. LK, which is the distance here, is equal to the square root of delta xk to the second plus delta yk to the second. Here you have the horizontal distance, then you have the vertical distance, and when you raise each one to the second power and take the square root following the Pythagorean theorem, you have the length of L sub k. In turns, it can be written as the square root of, for delta x sub k, you have f of tk minus f of tk minus 1 to the second, plus for delta yk, you have g of tk minus g of tk minus 1 to the second power. Now remember that if you have the Riemann sum and then take the limit, you're basically defining the definite integral. This is another use of definite integral in calculating the length of the curves. So, in general, if you have a curve starting at p sub 0 and stopping at p sub n, you can divide this up into smaller pieces and approximate each piece by line segment, then add them all together. We can also take the limit and use the Riemann sum and the limit and the definite integral. So if delta t sub k is very small, the length L sub k is approximately the length of arc P sub k minus 1, P sub k. By the mean value theorem, we know that there are numbers like T sub k star and T sub k double star in the closed interval T sub k minus 1 and T sub k such that delta x sub k, which is f of tk minus f of tk minus 1, is equal to the derivative of f at T sub k star times delta tk. In turns, we can write down delta yk with the same argument using the mean value theorem, everybody. So this guy, since y is a function of t using g, you have g of tk minus g of tk minus 1, which in turns is equal to g prime of tk double star, which is a point in the closed interval here, times delta tk. Why it is important? Because it helps us to make a calculation and drive a formula. How it's possible? Remember that L sub k is the square root of delta xk squared plus delta yk squared. Now, if you take the summation of both hand sides, this is basically the summation of, you just replace delta xk to the second power by the values that you have. Delta xk, which is defined as f prime of tk star times delta tk. When you raise it to the second power, you have to raise the right-hand side to the second power as well. The same for delta yk, which is the derivative of g times delta tk. Now you raise everything to the second power, and you can factor out delta tk squared, and then since it's square root of delta tk squared, you get delta tk outside your radical. Very good. So the length of the curve can be written as the definite integral from a to b of the square root of f prime to the second plus g prime to the second. And as you take the limit of delta t, it is d of t. So another application of the definite integral is helping you to calculate the length of this curve. Now I expect you to ask, what if we don't have a parametric curve? Suppose a curve is given by y equals to f of x on the interval a to b inclusive. So here you have your curve. You want to know what is the length of this curve. Remember that we're going to use the mean value theorem. And L, as we saw before, is the summation of the square root of delta x squared plus delta y squared. Using the Pythagorean theorem, this length here is delta x squared plus delta y squared to the second power each, and then take in the square root. In turns, you can factor out delta x. You can divide both of these to delta x to the second power and write this outside the parentheses. So you have the square root of delta x squared, parentheses 1 plus delta yk divided by delta x to the second power. In turns, it becomes the summation of square root of 1 plus delta yk divided by delta x to the second, and then you can write this guy outside the radical without the power 2. Remember that delta yk divided by delta x is nothing but the derivative of f at the given point in the closed interval. And this is basically the mean value theorem. Now, if you take the limit of the Riemann sum, L is the limit of the summation of delta x times the square root of 1 plus f prime of xk star to the second power. So when you're taking the limit, the Riemann sum or the summation becomes the definite integral, and the limit of delta x is basically your dx. So in general, if f has a continuous first derivative on the interval a to b, the length of the curve from a and f of a to b and f of b is nothing but L, which is the definite integral from a to b of the square root of 1 plus f prime of x to the second power dx. So let us summarize these two. The length of parametric curve, if your x is f of t, g is a function for your y, and t is bounded between a and b, then L, the length of the curve from a to b, is the square root of f prime to the second plus g prime to the second dt. And if y is a function of x, then L is the definite integral a to b of the square root of 1 plus f prime of x to the second dx. Remember that if x is a function of y, it means that x is g of y. You basically change this to g prime of y and dy. Don't forget to change these boundaries as well.